Hello, Nikita. Do you have any problem? Also, Anirban?
Yeah, so actually, sir, in this video, they said you have, sorry, you should be familiar with the basic Linux command. I'm not familiar with the Linux command, so what should I do?
Okay. In that case, I will provide a link so that you can familiarize with the basic Linux command. Okay.
Okay, sir, thank you.
Okay.
Hello, Biraj.
Yes, yes.
Anirban. Yesterday, actually Saturday, from whole day I'm working. That I have done the Ubuntu, the installation, the bash.c file in the program has been lost. I don't know how the command has been. Could you once again recheck the bash.c file of the
Uh, in the present moment, I can't look at the Basarci file since today is the setting up a case in an open form. So in this case, John has already pasted a Google Meet link. You can join that link. Okay, regarding
which
the
link? Which link?
installation error, I will send you.
Hello, Biraj.
Yes.
Yeah,
Yeah. Yeah.
I have joined the Google Meet link, but no one is allowing me to get in.
Okay, I will paste the link again.
Hmm. I have already applied for in, but no one is allowed to let me in.
Okay. Okay. I will.
Please allow me to let in.
Sure. Sure. I have just pasted a link regarding the installation error, so you guys can open that link.
Yeah, now I am in.
And I have to mute the what the that the Zoom meeting should be over, not it will be minimized.
You please leave the meeting and open that link. Copy that link and open the link. Okay.
Okay.
Pranay, is it okay if I share my screen for a second? I think I have some issue with my visualization in ParaView, and the same thing is happening with Gedit as well.
Viraj,
Re-
what would you see?
okay. Okay. I just missed it. So regarding the setting up a test case, cavity case in the open form, do you guys have any problem?
The thing is, I don't have problem with the test case and running the simulation, but the visualization bit in the ParaView, there seems to be a glitch or something with the ParaView.
Okay. Okay.
And
Like there might be a like blurry screen, right?
yeah.
Yeah, that is the problem of that is not the problem of open form. That is the problem of display error. In that case, you have to restart the PC and again type the paraform command.
Kinematic pressure file P and the
Got it.
velocity file U.
Okay, got it. Thank you.
Hello, Nikita. What Google Meet link are you talking about? Is it Google Meet?
No, Viras, this is Linux command link.
Okay, Linux command. Okay. Okay. Yes.
Yeah, I'm Geo Sebastian. Yeah, so the talk is happening in some other link because of some technical issues I could not. I could only rejoin now. I joined in the initial first session, but then after that I faced some technical issues, and only now I'm joining back.
Okay. Actually, like Professor Janini has talked about an overview of the CFD. So, in that case, we will provide you the recording.
Okay.
And you can see.
Okay. So now is it a break now?
In the meantime, you can watch the video.
Okay.
So, did you download the open form?
Yeah, I have that. The other day I joined Saturday. I think your team helped me to download open
Okay.
form.
Okay, I have provided a link
Okay.
where you can see the video and follow the commands. Okay.
Okay. I mean, is this link for installation or
No, for
after?
running the simulation in open form.
Okay. Okay. Fine. So right now, is it some kind of break in between?
No, right now, like everyone is following the video.
Okay, the spoken tutorial.
Yes, correct.
Okay, fine. Okay.
Hello everyone, Nikita as well. So I have provided a link, this CFD Direct, where you guys can see the basic Linux command and get used to it. Okay. So I will provide the link again, so you guys can go there and see what are the basic Linux command.
Hello, can I ask a question?
Yeah, sure.
Actually, I'm watching this file transport properties.
Okay,
Firstly,
okay.
there is a header form file header.
Yeah.
In some files, we use this location term, and in some files, we don't. So, is there any specific thing, or we can remove this or not?
What location are you talking about? Like
Uh,
gedit system
no,
control
the
date.
form file header in each files, the input
Yeah.
files of
Mhm.
like we can take the example of transport properties file.
Yeah.
There is a header form file, and we have written the format sky class dictionary, and in some other files the location term is not there, but in some files it is there. We are depicting the location like constant folder or something.
Yes, yes.
So
Because to denote on which directory it is presented.
but in some files we are not writing this. In
Okay, I
some
will.
files
I
we are
will.
writing this.
Yeah, I will guide you the steps in like let's say 5 minutes, and
Okay.
I will also talk about
See,
that.
one more question I want to get your attention to. The
Okay.
object is like transport properties.
Mm-hmm.
Whether we use this same name or can we use some different user-defined name for this, or it will be same as that of the file name or different.
No, we have to define it as a transport properties or something.
Okay, the name, the correct spelling that
Yeah, the
is used.
correct spelling. It is the C++, right? So it is
Okay.
very case sensitive language. So even if you miss to capitalize some words, some letters, then it will show an error.
See, we can create an object for any class, fine. So
Yeah.
whether we have to use the same object name that is depicted in this file, or can we change that?
So actually, like if you want to make some like let's say a file like let's say transport properties, so you
Yes.
have to define the same class.
Okay. The same. I have to use the same name as the object
Yes.
as that of the file name.
Yes, correct.
Okay. So if I change this transport properties file name to something else, I have to do it
No, no, no.
in.
It won't work.
Okay. It is defined in the solver that the name would be transport properties.
Correct, correct, correct.
Okay. Thanks.
Sir, I am Pratik Kumar. Actually, I have classes, so I missed the first 1 hour class, and I am going to miss the next 1 hour class also. So, when will be the recordings available? Is it available today night by tonight? So I can watch.
So you have missed the last session.
Last 1 hour class, and now from 12 also I have class.
So, Pratik, typically recordings, we will only decide at the end of the course if we want to release it or not. Okay. So, it is best for you to attend everything because due to some logistic things, sometimes we don't release it also. So, it's best you attend as much as possible. Okay.
Yeah, Viraj, one small question.
Yeah, yeah.
In this, actually, I want to know how to change the FP schemes. There is in that block, there is a control date.
Yeah.
There is in text editor. How we can change the FP schemes? All these things I want to know. If possible, can you please explain those things also?
Okay.
So I think those are advanced things. So we will slowly take you through that. It's best to kind of follow through with
Yeah,
these.
okay. At the end of the workshop, we will get it, right?
Yes, you would know how to do that at that point. No problem.
Now I'm going to demonstrate in my own system. So first of all, go to the run directory. So in that case, type this command cd FOAM RUN. So you will go to the run directory, and after that, copy the tutorial. Incompressible. Inside incompressible, there is an icoform solver. So remember to put the F capitalized. So otherwise it will show an error. And after cavity, you have to put the dot sign in order to specify the destination folder. So inside that, go to the cavity case and let's see the boundary condition. So in the boundary condition, there is a moving wall, right? So the upper wall is moving in the direction of x-axis with the velocity of 1 meter per second, and the fixed wall is given no slip condition, where at that location the velocity will be 0, and front and back is considered empty since this is the 2D case. So close this file and go to the gedit 0p file. This is the pressure file. Here the zero gradient is given since the value is the same as the adjacent cell. So let's go to the gedit pressures file. So zero gradient is given, and zero gradient is given for both moving wall and the fixed wall since it sets a value same as the adjacent file. So let's go to the control dict file system control dict. So in the control dict file, icoform solver is used, and the end time is 0.5 second. That means the simulation will stop at 0.5 second, and the start time is 0. So I will also close this file. So run the block mesh command. Okay, I forgot to go to the block mesh. So there are 8 vertices, as you can see, and the 2021 means there is 20 divisions in x-axis, 20 divisions in y-axis, and 1 division in z-axis. So run the command block mesh. So the block mesh has been generated. Actually, the 400 cells has been generated. And after that, run the simulation by typing icoform. Remember, some participants has placed the space sign between the ico and form. So please don't do that. So the simulation has been ended. So you can see the result here in the paraform. Click on the apply button, and in the VTK block colors, press U button and run the simulation. Did all get the same results as I've shown? So this is the result I've got after running the simulation.
Okay, so I think most of you have got it. Anybody who's not got it at this point? So if you can type yes if you finished it, be helpful. So mostly yes. So what I will do here is, so I would like you to, what I've done is there are two main input parameters, which is the velocity and the delta t. Okay. So I would like you to pick maybe some value in the lower end, some value in the middle end, some value in the last, and simulate 3 simulations. You can take a screenshot of your original flow and the 3 different flows. Okay. And at the end of it, tell me what I would like you to share your screen with all the 4 pictures, and maybe you can put it in a document, paste it in a document, and then maybe you can tell me what is the difference that you see. Okay. And be flexible. If you just don't want to change delta t and only the u values, yes. If you want to change the u, you want to change delta t and keep u constant, that also is fine. But we want to see why and if the simulation looks different to whether if it doesn't. Okay? So we will give you a very quick 20 minutes to 25 minutes to be able to do this. Paste it in the document, keep it ready, and then I would maybe randomly pick on you to show me and talk about your results. Okay? So I will keep this, I think. Viraj, do you have this document on you, or I probably will.
Yeah, I have that document.
You have it? Can
Yeah.
you post it into the chat window so that
Okay.
I mean, they can download it from their side also for later references.
Sure, sure, ma'am.
Apologies, I was not muted before when I got the call. Fine.
Hello, everybody. I have shared the Google Drive link for your future reference. Hello, Ali. In order to decrease the Courant number, you either have to decrease the velocity or delta t. Okay.
Yeah, good, Ali. You picked it on because that's the whole idea of this effort, because we need to understand we can't randomly change these things without consequences. Okay, so that's a good observation you made. It's a good start.
Hello.
Is there a command to save every new iteration that we did while changing the velocity and delta t into a different directory? Because I think all the time steps are getting together and the simulation is getting a bit messier.
Like, did you change the right interval?
I changed the velocity and also the delta t, but
Yeah.
then all the simulation results that are forming in the same folder.
Yeah. This is the in the open form. It will write inside the folder, right? Inside the case. So that is the like a structured way of pasting the pasting the results into the case folder.
But is there a direct command to every time save a new iteration into a different folder?
Yeah, you can change the right interval. You can change the right interval value. Like, let's say if you want to paste the simulation result, average iteration, you can type like, let's say delta t. Like your delta t is 0.001. You can say the right interval as 1. Okay.
I have completed the default 1 and 3 cases from this. Now what?
So you have already done the simulation.
Yes.
Okay. So make a report that contains the 2 or 3 plots, and
Okay.
you can even present the screen.
Okay, fine. Thanks.
Hi Viraj, I am not able to run the block mesh detector actually.
You are not able to run.
Yeah, block mesh. Yeah.
So in that case, type block mesh, BLOCK.
Yeah, I have typed it and I have showing some error. I will just post it. Is it okay?
Sure, sure. Okay.
Yeah, Viraj, I was doing the previous mesh. What did you do? And when I'm writing mkdir slash p open form, I don't know, showing the mkdir is missing operand.
If you have already, that is the command to create a run directory. If you have already created the run directory, you don't have to do that. So I just didn't do that part. So in that, if you have already made the run directory, you don't have to use that command.
So what command should I use directly? cd command.
Yeah, directly go to directly copy the directly use cp space hyphen r and form tutorials incompressible I
Okay,
form cavity. Yeah, that command. Okay.
okay, okay. Thank you.
Looks like there is a set
Yeah,
of results.
I have posted
What to do that?
my error.
Viraj?
Yeah, yeah, Paritosh, right?
Yeah, Paritosh.
Yes, the main problem is you in the Linux command always name the case with underscore. Don't put the space sign. So that's why it shows that kind of error. See, you have put the name lead driven cavity. You have to put underscore in place of the space. Okay,
Okay.
and you get that error.
Okay. So now it will run after
Yeah,
that,
it
right?
will run. It will run.
Hello, Viraj.
Hello.
I'm getting an error like set document metadata failed in the initial stage itself.
Did you use
Yeah, the
gedit?
same thing stuff.
Yes, gedit.
Which
This the
operating
CD
system
sucks.
are you using?
This is Windows 11.
In that case, you can also use notepad.exe in place of gedit.
notepad.exe.
exe, yes.
Okay, thank you.
So may I ask how many of you have been able to finish? Can say yes or no.
Ma'am, I have prepared the images in a PDF format.
Okay. If you can maybe share your screen, that would be
Okay, ma'am.
great. Okay. So
Yes, ma'am.
so Sonu, do you want to show me if there is any difference from case to maybe you can make it smaller so that we're able to compare two, three images.
Okay. Ma'am, actually, I have taken snapshots and made a Word file out of it.
The 100% on the PDF, you make it about
Yes. Okay, ma'am. Okay. Let me do it.
while Sonu is preparing everything, let me share screen. So very quickly in OpenFOAM, you followed a certain path, file path name, right? Which said incompressible, certain other things. So the first thing that we need to understand is OpenFOAM has different sets of solvers. It keeps different folders for different sets of solvers. And the solvers that are categorized are incompressible, compressible, heat transfer, multiphase, Lagrangian, discrete methods, combustion, DNS. There are boxes. And in this case, we would largely be talking about incompressible, heat transfer, multiphase. We are also, and most of the applications are in these, right? We do talk about a little bit of compressible. From basic, we would probably be using the Laplacian form. And I think we have a lecture on discrete element method. Okay. So today we have started you off on incompressible, which is the most basic form. And under incompressible, there are different solvers, correct? So there is boundary form, you can forget about boundary form. There are four main solvers that are there under incompressible: icoform, pimple form, piezo form, and simple form. So typically in OpenFOAM, the solvers are appended with a name called form, with the first part talking more about its function. So icoform, which is what I think you've used for the first spoken tutorial, is incompressible form. Okay. Then you have simple form, pimple form, and piezo form. So these are all different ways of solving. You would have heard simple algorithm, piezo algorithm, and all that. So these are algorithms using that. Okay. So there are typically four solvers. Okay. Okay. So now coming to the next question. How are these solvers different, right? So my first question is, if I give you right now we have done a spoken tutorial wherein lid-driven cavity was the problem and icoform was used. But if you were given a lid-driven cavity problem and asked to solve it, you would have to choose a solver. So you would have to know what is the capability of every solver. Okay. So typically, the difference between these solvers lie in basically these two terms. Okay, so you have the conservation momentum equation, correct? So in the momentum equation, you have the transient term. Okay, and then you have turbulence. Okay. What are these two things? If you have laminar, there is no additional force which is attributed to turbulence. So this term is not there when you're solving it as pure laminar. But when your force or flow is more, there is a turbulence modeling that comes into perspective. So certain solvers can do turbulence. Okay. And the other aspect is whether it is transient or a steady state solver. What do we mean by a transient or a steady state solver? Anyone can tell me?
I mean, steady state solver, the temporal term is not there, but in transient it is there.
Okay, so for example, let us talk about the lid-driven cavity problem, right? Is it a transient or a steady state problem?
And after some time, it seems that it is steady state, but icoform, I think, transient solver. So
My question is problem independent. I said, is lid-driven cavity a steady state problem or a transient problem?
If it has time steps,
It's a steady state.
it's
it is steady state
transient
problem,
problem.
but we are doing it with a transient solver.
So is that wrong?
Not actually, ma'am. After some time, I think we are on to that solution. It is not changing with time.
So maybe in the chat window, everyone can first type first question. And I want all of you to kind of venture. Yeah, some of you have typed. So some of you, so I want to know if the lid-driven cavity, the problem itself, forget about how I'm solving it. I solved it to the icoform. Is it transient or a steady state problem?
Ma'am, can I just add something to it?
I'll let you 1 second. Okay, I'm just looking at what people, it depends on the Reynolds number. I don't know what that means, but yes. So a lot of you have said it's transient. Steady. Okay, there's Harsh which says it's steady. Okay. So that is very interesting. It can be steady state or transient. Very good, very good. So Arun, can you tell me why do you think it can be steady state or transient? Arun? Or maybe Vipul? You say it can be both.
We can take any initial conditions. The steady state will be set.
Okay. So I would look at this very, okay. Okay, I appreciate all your answers, right? So this is some aspect which has to be very, very closely thought about in CFD. So I have this box, okay, and like somebody said, it is stationary. So let me think that I'm in a chemical factory, okay, and there is this chemical in this box which has to be stirred at a particular velocity. So I'm there, this box is there, and imagine there's a conveyor belt on the top, and the role of the conveyor belt is to move at a constant pace velocity. Okay, so right now what happens is you have stationary liquid, which is your initial condition, and then this starts to move. And it runs for 10 minutes, and then there is this circulation that has now become constantly moving. So yes, steady state means your flow field is unchanging with time. That definition all of us are clear with. So after 10 minutes, my flow field is steady. It's rotating the same way. Okay. Now the question was, is the problem steady? Okay. So then you should first ask the person, what is your interest or your question of interest? What do I mean by this? Now, if I'm in that chemical industry and I say, listen, my time is important. I need to get to this steady moving velocity, okay, very quickly. Okay? And my interest is how this domain velocity is, whether this constitution in this steady region, is it mixing properly? That is my interest. Okay. So or let me rephrase it. You put color dye in this, right? And I want to know whether that particular domain in the steady region has that particular shade of pink. That is my interest as an industry person, right? So that means my requirement to you as a CFD person, the CFD expert is, I don't care about whether it takes 10 minutes or 20 minutes, but I want to know what is the color of that particular part of that flow. Dye wahan pe pahuncha, whether it is pink in color, that particular shade. So that means for you have to anyway reach only that steady state part, correct? You are not interested about from that stationary, how it goes to steady, you are not interested. You want to come to that steady state part. So then, for you, steady state simulation is far simpler. less time consuming. Why? Because that transient term is not there in your problem. Okay. But I will give you a caveat. The steady state numerical solver is more unstable. Why? Because from 0, you're having to go to that other. So typically, much simpler problems, you can do steady state simulation very quickly. But for more complex problems, typically they'll start out with transient. Okay, and then they will swap to steady. There are other reverse things also being done, but it turns from case to case. Okay, coming back. So as an engineer, I have given you the requirement that I want to know what is the distribution of the color at that point in time. Okay, so that means that you have to start by saying, what is the question that you have for me? Now, if I'm a person, industry person, which says, for me, time is more important. I don't want to start in 20 minutes. I want to start in 10 minutes. I want to reach that steady state in 10 minutes. Then for you, what is important is this initial stage of stationary to that steady state. How quickly can I reach? What is the velocity that needs for me to get? That time window becomes more important. Then for you, you will have to run that transient simulation to track the time from 0 to that point. Okay, so question of, in this case, your end story, the problem is steady state. But your simulation depends on what is being asked of you. Okay, so right now you have done it with the transient solver. Okay, so that was the question. Okay, so now coming back to this step where I said transient versus whether this is turbulence, right? These are the two parameters which set apart these solvers. So let us look at, okay, I'll come back to this. So solver capability wise, right? Solver capability wise, you have what is called a icofoam, which is a transient solver. Yes, but it doesn't do turbulence. Never mind, ours is a laminar problem, right? Okay, so can I run the problem with any of the other solvers? So coming back to my question, your task is lid-driven cavity solution. But you have to choose the solver. So would you be able to choose from any of this? You'll have to choose whether any of the other solvers will do the work. So I said this is a laminar problem, right?
Yes, we can choose any other solver just to we will solve the turbulence part.
Correct. So you can use any of these solvers. A transient solver will do, like I explained to you, right? You would just run it up to the point where it reaches steady state. If steady state is your interest, you would run the transient part if the initial part is of interest, correct? Now, if you were to given the task of running a transient problem, would you at all choose simple form?
No.
No. Why? You could add a temporal. Technically, in open form, you could add a temporal term and solve it. Yes, you can. But the thing that you need to understand is, so these are the combinations. If you want to run a transient problem, then you can choose icofoam, pimple form, or piezoform. You can do simple form with a transient term, but it is a little bit more complicated in open form only because there are several libraries. And typically, adding transient terms means you should have a solver which is capable of handling some of those schemes. So ideally, adding terms is not suitable. You choose what is closest to your requirement. Okay. Now, if mine had turbulence, would I choose icofoam? If mine had a turbulence, I won't, because I would have to add turbulence model. See, these have turbulence. I'm just removing the turbulence capability. That is easier than adding a whole turbulence model. So I can stay away from icoform. I will go to pimple form, which is a transient and a turbulence problem. Okay. So always keep your edits in open form to a minimum. Okay. So now what we will try and do is we will do the open form part, which is the icoform solution that you did in simple form. Okay, so that means you are shifting from a transient solver to the steady state. Right now, my interest is only to see the final velocity plot, correct? So I'm going to not be interested in transient run. So I'm saying I'm going to do simple form and I will change turbulence to laminar and just run it. And let us see if we get the same result. Okay. So before we do that, Sayantan, you had a question, right? Let me come back to you.
No question. It's just the initial question you are asking whether it's a steady or unsteady. I just want to add at some point, but you have covered it.
Okay, great. So what we will do, Sonu, we will come back to you to show your plots and colors. What I want, Biraj will now walk you through how to do the same problem, not in icoform, but in simple form, which is a steady state solver, meaning it has no transient terms. Okay, and this turbulence capability, you will remove it and say laminar and run. And let us see. And Sonu, you can add the same picture also into that plot. Okay. And I will come back in 15-20 minutes to check on all of you. And in this time, I want all of you to kind of catch up, finish up all your simulations. Okay. And I will touch base with you in about 15-20 minutes. Okay. Biraj, go ahead.
Hello, everybody. So I will send a Google Drive link, which encompasses all the commands you require. So I've just posted a link. Please, everyone, check. Okay, go to that Drive link, and there is a presentation that has all the commands that you require to simulate a cavity case in simple form. So go to that PPT. First of all, go to the run directory. Okay. To go to the run directory, type cd $ space $ home run. I will also present at the same time, so that I see all some of the people are struggling to use Notepad in the Windows. So you can use this command. First. So you can use this command in place of gedit. Okay. In place of gedit, in gedit you put the command gedit space system control dict. But if gedit doesn't work in a system, type this command and and type enter. In my system, I don't have Notepad, so that's why I use gedit. But if you are Windows users and gedit is not working, use this. Okay, use that command notepad.exe and give the destination of that file, if it is inside the system or if it is inside the control. So do that. Okay, so after you go to the run directory, I will start from the first. Okay, type this command cd pom run. Type this command and you will go to the run directory. See, the run directory is shown. And after that, just copy and paste this command, the first command. So go to this P. After you type the command FB solution, this FB solution, type this command pref cell 0, pref value 0. Okay, this pref cell 0, pref value 0 in line 41. Do not delete any file. Just type this command pref cell. Note the capitalized letter 0 and pref value also 0 in order to because we have used zero gradient boundary condition. So that's why we have to use this command. Okay, inside the FV solution file, and close this file and go to the terminal and close it and go to the momentum transport file. Okay, copy and use this paste. Okay, so momentum transport file. See, RAS means Reynolds average simulation. So we don't want that simulation. We want laminar. So we have to use this command and control save. Always remember to save it. Save and close it. And after that, change RAS to laminar to simulate laminar case. After this, go to the control dict file. Okay, so copy this and paste here. Control dict. And so there is this 47 to 64 commands in that line. So you have to select it and delete this. We don't want this because it is because why we are deleting this file is because this is previously implemented in another case. Now we want to simulate in the cavity case in a simple form. So that's why we are deleting it. Okay, so control save and close it. After this, go to the transport properties where we can define the kinematic viscosity. Okay, gedit constant transport properties, and you can see the Newtonian transport model, and this is the kinematic viscosity. So this is the dimension of the kinematic viscosity, and here 10 to the power minus 5 is defined, but in the cavity case we have defined it as a 10 to the power minus 2. So remember to change it, and after this close it after saving it. So now we are set. Now we can run the block mesh command in order to run the mesh. Okay, block mesh. So the mesh has been created. The same mesh, see, you can see the 400 cells, right? So this is the same mesh we have done in the cavity case, and now run the simple form instead of icoform, because this is the steady state solver. Now we are running the same kind of simulation in the steady state. Okay, so type this command simple form. Now simulation has been converged. Now let's go to the para view. So in order to do that, we have to run this simulation. We have to run this command paraform. So click on apply button and click on the U button. Okay, and run the simulation. So you can see. So this is the same result you have got in the using the icoform solver. Now we are getting the same result using the simple form solver. So this is the process. So you can see the same simulation, velocity contour in simple form and velocity contour in icoform. Thank you. So if you guys have any problem, place that queries in the chat. We will help you. Okay. Thank you guys. Make sure you run the simulation inside the piece daily case. Okay.
Could you tell me why did we delete the code lines from 47 to 64 inside control dict file?
Okay, in that case, they are plotting, they are using the streamline function. So we don't need that because it requires the k epsilon value as well. So we don't require that. This is the laminar case. So we have to remove that line. Okay.
And what about the kinematic viscosity? Why did we change that?
Okay, in the pitch daily case, the kinematic viscosity was 10 to the power minus 5. And in the cavity case, the kinematic viscosity is 10 to the power minus 2. In order to set the same condition, we have to change it. Understood?
Okay, so just to get the same
Yes,
answers.
correct. In order to get the same result, you have to set the same boundary condition, same transport properties, right? So
All right,
we
yeah.
have to do that.
Got it. Got it. Thank you.
Okay.
So have everyone been able to finish? Would we wait for a couple of minutes, maybe 5-10 minutes? Okay, there are still some errors that are coming up. So we'll wait for about 5-10 minutes for everyone to catch up before going on to the next step.
Hello, Meenakshi. So you got that error. It's because the paraform doesn't work. In that case, I think you have also come in the previous session that we have already told you that to install the paraview externally, and you can use that command.
Okay. Externally, but how to access it?
Okay, you can access it by using the command touch space result.foam and go to the paraview and locate that file and open that .foam file, and you will get the same result.
Okay. Thank
Okay.
you.
Hello?
Yeah, like my simulation is not running. As soon as I press play button, the paraform is getting closed.
Paraform is getting closed.
Yeah,
Like, can you share the screen? What has happened?
sure. Yeah. Is it visible?
Yes, correct. I think
Yeah, I'll try it once.
okay. Close. Yeah. And run the simulation in the play
Wait a
button. Go to the play.
Wait a second. Yeah,
Yes.
it's getting closed. That's it.
I think the error is because of like your boundary condition. Please check. Like what you do is cd type cd space dot
Okay.
press enter
Yeah.
and delete that file, because I think you have missed one or two steps, so that's why it shows that error, because you missed the copying of that boundary condition into your pitch tail case.
Okay. Yeah. Sure.
So what you do is remove this pitch tail case and again start the steps from the start.
Okay. Yeah. Sure.
Sir, can you please help me as well?
Like what is the problem? What error did you get? Like I have already showed the demonstration. So what you do is I have also gave you the PDF file where
Yes.
it has
Sir, yeah, actually, I tried until the step.
Okay, until what step? Like
Um, I have shared the screenshot as well in the chat box if you could see.
okay, I will see. Hello, Uma Reddy.
Yes, I got the this moment transport up to that, sir, but mesh not created in that one.
Okay, mesh not created. So after that, you can. So on which step are you in? Like,
Sir, I have shared you the screenshot. Could you see that?
still not visible. Can you share again?
Sir, I have directly
This one
shared to
came,
you,
sir.
or do you want me to do the everyone?
You can share the screenshot.
Yeah, I have shared you, sir.
Okay. I will see. But first, I will look at the Uma Reddy case. So you have already done until this step, right, Uma?
Yes, sir.
So what you do is just replace RAS to laminar in the 17 line.
17 line.
Yeah.
Replace here. RS.
Replace LAMINAR. Laminar.
Laminar.
But replace that.
Enter.
No. Replace that. RAS. Delete that.
Okay.
Yes, correct. And also semicolon. Delete. And put that semicolon in the after laminar, because it shows the end of the line. In the C++, the semicolon means the end of the line. Okay. Save it and close. Now you can proceed another step. Okay.
Okay, sir.
Now you can unshare your screen.
Hello, sir. Sir, I'm not able to open my block mesh dict. How can I open this?
So in order to do that, you can use gedit or notepad.exe system and blockmeshdict.
So can you write this in chat box?
Sure.
Okay, thank you.
Sir, could you see my screenshot or still not yet?
Still not visual. What you can do is share the screen.
Yeah, sure, sir.
Sir, how to delete the pitch daily file?
Hello?
Hello. Yeah.
Yes, sir. Is my screen visible, sir?
Yeah. Still. Yeah. It is visible. Just second. Just wait a second. Okay.
Yeah, sure, sir.
Okay. Now. Okay. CPR cavity. I think you have not done the previous case. Did you also do the cavity case following the spoken tutorial? So that's why there is an error.
Oh, okay, sir.
Did they not miss the dot at the end?
Okay.
Sir,
After
then
there is a space.
Sir? Sir, actually, I was trying to install the OpenFOAM during that period. So,
I think C has not this copied the cavity case.
okay.
Viraj sir, I'm using my OpenFOAM in Windows 11. So, like, what should I open this? Get gedit or
So if gedit is not working, use notepad.exe. Okay.
Okay, sir.
Okay. Hello, Swapna.
Yes, sir.
Can you yeah, down, scroll up, type Control C. Okay, you didn't make the run directory, right?
No, sir.
So in order to do that, I think this will take a while. So what you do is I will post a Google Meet link and you can
Yeah.
join.
Oh, sure, sir. Thank you, sir.
Okay.
Thank you so much.
So I think, can I just come in a bit? So everyone, maybe we can discuss a little bit. I'll try to finish what I have to say in 10 minutes so that everyone gets a perspective, and then we will finish the session from my side so that all of you can, with Biraj and John's help, complete the rest of the procedure. Otherwise, it feels very incomplete to be able to do that. So just hang on. So Sonu, are you ready with your snapshots?
Yes, ma'am.
Wait, can you share your screen, please?
Yes, ma'am.
So Biraj, by the time, maybe you can take Swapna to the Gmeet and then finish that error work.
Okay, ma'am.
Sure, ma'am. Thank you.
Here's this file. Is it visible?
Yeah, it's visible.
This is the default case.
Yeah, when you move down, so there's a velocity of 5,
Yes.
velocity of 15, and there is a velocity, right?
14.
So can you come further down? Which was the velocity?
This is the default case of icoform, and this is for simple form, the first case.
Great. Okay. So everyone, can you at least see if you go up to the second row soon? Right. Good comparisons. So if you see, can you see a difference between the default case and maybe what is there in the second row first? And what would you think the difference is? Anyone can probably unmute and say. What do you think? Just looking at the flow field.
As the velocity is increasing, the higher velocity cells, where the velocity is higher at the centroids, are shifting towards the right of the cavity.
Correct. So, in a way, would you need lesser time steps or more time steps without looking at what settings you did? Would you need lesser time steps or more time steps? Or let me read. dt ka value, should it be low or high?
Ma'am, if we are lowering the value of time interval dt, then I think the number of iterations required are more.
Okay. No, but my question is, if say my velocity is 10 meters per second instead of 5.
Yes, ma'am.
I need a lower dt or a higher dt?
Ma'am, to follow the CFM conditions, I have to calculate those values so that the CFM, the
So you
proven number
understand
is.
what CFL is, right? So everybody else, can you type what you understand Do you know what CFL is? Yes or no? Do you know what CFL is? No. Okay. So there's a good half of no and yes. So let me, so Sonu, let me share my screen for a little bit. Maybe I can explain to them.
Okay, ma'am.
Yeah, you
Should I
can.
stop
Yeah, you can stop. Thank you. Thanks. Okay. So let us first understand what CFL is, since many of you also know it. This is how I picture it, right? So let me see that I have a cell like this. Or let me even think I'm standing in front of, a window. And I'm seeing, say, a bird fly by, right? And I keep my eyes closed for 10 minutes. And the bird flies by. Will I be able to see the bird? No, right? I will think that the situation, there is no bird. If I have closed my eyes for not 5 minutes, but maybe 1 minute, and I open it. So every 1 minute I'm opening it, right? So the bird flies by within that 1 minute, I say, there is a bird, right? Now I open every 30 seconds. Then I see that the bird has come, sat on the window, okay? Maybe hopped twice and then gone out, right? If I blink my eye every 10 seconds, I see that how many times the bird flaps its wing to come and sit down in the first thing. So what is the idea? Some phenomenon, right? Whatever frequency of the phenomenon, I have to have a time window suitable to capture that phenomenon. Okay. So in the concept of Courant number, if I have a cell is my control volume, my visualization window. So then a particular flow, if it has a particular velocity, right? That means that event is crossing through that box in that time. So if I have to, if you remember, you made choices or approximations in schemes. You took gradient, right? What did you say? You presume that this is going to be somewhere midway between these two values, correct? So you're approximating. When you're approximating, you should be sure about this value and this value is correct. That means you have to calculate these values correctly. But if I have to capture this value in every cell correctly, that means I have to do proper solving of all the terms, which is also the temporal term, within this cell properly. Okay, that means I have to capture the event in that time window. Otherwise, it won't be correct. Correct? So, Courant number says or is defined as U delta T by delta X. Now, what does that mean? U delta T is a distance. If my flow is of velocity U and my time step is delta T, it will travel a distance of one cell length. Okay. So U delta T by delta X should at the max be equal to 1. What do I mean to say? In that time step that I am going to do an iteration, when I do a calculation, I'm actually saying stop, I'm going to do calculation. I'm putting a meter or a reader into the flow to get the value. So I'm saying, listen, within that delta T, I'm going to put the meter again, and it should have moved at the max within one cell. It shouldn't. That's when I will get, if it is within, if it had traveled 5 cells by the time I put a meter here, it's pointless, right? So Courant number is a measure, and CFL condition basically gives you this criterion. It says U delta T by delta X is maximum, is ideally 1 is advised. Okay, so now if your velocity increases for a same delta X, then your delta T should ideally be a little lower, so that you're able to capture it within that cell distance. Which is why in that assignment you were given different U and T combinations. Okay. Now some of you would have just probably changed U without changing the delta T, and your Courant number would have become high. then immediately it's an indication that if it is going above 1, that you have to pull down your delta T. For more complex cases, people will have to adjust their mesh. They will remesh with smaller meshes and then adjust their delta T so that this Courant number comes below 1. So it is a very dynamic case. Okay. So this is the importance of trying different U, delta T, and of course, we have not taught you block mesh, so we have not asked you to change the mesh. You can change the mesh. If you all go to the block mesh file, you can make it a finer. This is an activity you can play around. If you make it, instead of 50 cells, you make it 100 cells. How does this resolution change? Does it make it better? Or after a point, there is nothing that is helpful. Okay. So these are things you have to understand. Okay. So what are the things that we have learned today, right? In today's activity, first of all, we have learned that we have something called a Reynolds transport theorem, which is necessary to convert a systemic law into a control volume law. Okay. Then this governing equation has the form of a transport equation, which has advection and diffusion terms. And choices for schemes of these diffusion terms become very important. Okay. And diffusion as well as advection schemes have to be solved by a solver. Okay. So if all of you open up your files, there are 4 folders that are there. What are that? Block mesh, control dict, FV schemes, FV solutions. So FV schemes is where you can play around with your scheme, advection scheme or diffusion scheme. FV solutions is where you will choose the solver, the matrix solver. Control dict controls your write time, print time, all of that, right? Block mesh controls your meshing. So this maps on to your exact CFD methodology, which I told you about, correct? So we talked about schemes, we talked about how algebraic equation comes, matrix comes, correct? Then we did a simulation with OpenFOAM, basic lid-driven cavity simulation. We saw that this is not that icofoam is specifically for lid-driven cavity. You can use any solver in OpenFOAM to do that, provided you tune it to the problem requirement. Okay, so we saw icofoam and we also ran it with simple foam. We saw that the results does not change much. But if you're running a transient solver, you are having what? A delta T term, correct? Because it's transient. So icofoam ke liye, there is this U delta T by delta X, which is a Courant number. So you would have to use different delta T's to keep the Courant number less than 1. We've understood all of this. Okay. So then we have also changed turbulence to a laminar because that is also an important parameter to change. Okay. So of all of this, do you guys have any questions in this overview that you have seen of incompressible solvers? We have talked about only incompressible solvers. Any questions now you can ask. Okay. So now we have kind of stepped you on to what is the background of CFD. How does OpenFOAM mirror the CFD process? We have taught you how to start and run a simulation in CFD and understand steady and transient requirements. What do you mean by steady simulation, transient simulation? Which solver to choose within the incompressible domain. Okay, so with that, today my session is done. Afternoon you will start with meshing, but now I will let it be to Biraj. I want all of you who have come late, who have not installed properly, all of you to sit here, catch up with everything before the second session. Okay.
Ma'am, I have one last question. Can I just
Please go ahead. Yes.
Yeah, I'm just thinking aloud. So regarding this Courant number, is there any possibility, any kind of flow where we will deliberately make sure your Courant number is greater than 1? For example, maybe we are simulating an ocean or maybe atmosphere.
Okay. So typically, I won't try to make it more than one. But so there are certain problems, complex problems, where I need a very quick initial guess.
Yes. Okay.
So in those cases, the problem is complex. So I cannot do a steady state simulation. So I do run a transient, but I am not very particular about my delta T. Okay. So then I generate a very quick delta T and a U profile. Okay. That U profile will go into my actual really resolved simulation with a proper delta T. You understand what I'm saying?
Yes, yes.
So those are the cases where I will compromise. Because see, otherwise in the original very resolved simulation, I will start with a zero velocity because I don't know my velocity estimations in the entire domain. But that is not really helpful for me at this point. Then I will, and steady state is crashing. So I will do a transient. I will not bother whether my Courant number is more than one. I will kind of let it run to give me an initial velocity estimates. And that U file I'll map onto the initial condition.
Okay, that's like a better initial guess.
Absolutely.
Okay, I understood. Thank you.
Anybody else?
Ma'am, I want to ask one question from fundamental equation, Navier-Stokes equation. When we take the Navier-Stokes equation, then we write the del rho over del T. Then after we convert into generalized form, then we write the del rho phi into del T.
Correct.
So what's makes the difference between because we introduce the flux in this term or some other thing?
So del rho, see, do not look of, okay, I understand where your confusion comes. Leave the conservation equation, conservation of mass out of the picture.
Yes, ma'am.
Only momentum and energy are transport equations. So when I wrote del rho phi, I'm only talking about the transport equations and not the continuity equation. But in some textbooks, you will see that phi term written there, but they will say phi is equal to 1 for continuity equation. That means forget it. Okay.
So I read in some books that's if we don't take the phi term in the equation, that's called the generalized equation. If we don't take the phi term, that's called the non-conservative equation. So what's the difference between conservative or non-conservative with respect to the phi term?
Nice. So, see, I think you're getting confused between 2-3 terminologies. First of all, one terminology is conservative and non-conservative. Conservative form means none of the variables are outside the derivative. So sometimes you've seen this for the divergence term. You will see something dot del the divergence u, correct? For the adjective term. That means outside the derivative, you have a term. Conservative form is keeping everything within the derivative form. Okay, because that involves some, discretization related things. I don't want to get into that, but everything is within that, partial derivative term. Everything is inside. That is conservative form versus non-conservative. It will also have phi. Okay. Now, if I'm saying phi is equal to 1, that means I am just saying that in the generalized form, if I want to write my mass conservation, which has no, what do you call it? No phi within the time change. It's only dou rho by dou t.
Yes,
then I will call it as generalized form with phi is equal to 1. Typically, that notation is not suggested. Okay. So don't look at it in that form. Conservative, non-conservative is very well known. Sometimes non-conservative form of writing is much more better for your CFD coding. Okay. But this phi is only like a way people write to make things. So even in my lecture, I've only shown that phi term only for the transport equation. What is transport? Only momentum and energy equation. It is not for the conservation equation.
Okay, okay. So we should not consider the conservation equation right in this equation. Just conservation, just focus on the momentum equation, like transport equation.
Yes.
Okay. And one more thing we are using in turbulence, like rho u dash into v dash. So we consider like just a momentum of flow in u direction, and the disturbance occurred on y direction, and we want to connect both of coordinate with these things uh, in physical world. In physical world, I want to see it.
Acha. So typically, okay, this will take me a whole lecture, which I don't want to get into, but I will tell you very shortly what it means, right? Typically, when you feature turbulence, it's like these kind of disturbances in the flow, correct?
Yes, ma'am.
So if I'm moving my hand like this in the disturbance, there is a disturbance in the u direction, there's a disturbance in the v direction, correct?
Yes,
So,
ma'am.
typically, disturbances propagate if it is a combination of u prime and v prime, meaning disturbances in this direction and this direction will propagate. Very shortly put, there's a lot more complexity to it. So that u prime, v prime product is the main contributor. Okay. So now how do I feature? Now, this is a very complex movement. How do I feature it in my physical simulation? So what do I say is that this movement is kind of a resistance to the flow, correct? So I will model it as a viscosity term, additional viscosity, not just my flow viscosity. So I say there is a flow viscosity, a fluid viscosity. The property of the fluid has a viscosity. But I will call this turbulent viscosity. This is like a viscous force.
Okay.
And a disturbance. It is a force. So I put that viscous force. You remember there were two force terms. One is surface force and a body force.
Yes,
right?
ma'am.
So for the surface force, I say, okay, fluid viscosity is one force. Okay. But this turbulent viscosity is also a viscosity or a force generating term. So the main thing that turbulence models do is they will say this disturbance is a kind of force, and they will put it in terms of mu dou u by dou x, dou v by dou x. You understand?
Yes, ma'am. Yes. But these forces lie in two directions, in horizontal or vertical directions. So we should multiply on it, or because I'm confusing on this multiplication.
So I will suggest, because this is a whole lecture, I will suggest look at Reynolds averaged Navier-Stokes equation. Okay.
Okay.
Because that is what this averaging Rand's form of the equation talks about, this exact question of yours. Why u prime v prime product is coming.
Okay. Thank you, ma'am.
Anybody else?
Ma'am, I had a question. What is the difference when we are using a turbulent model to solve a laminar equation?
We are just, like I said, putting this mu t term, that term to 0.
So we can use a turbulence model equation to solve a laminar equation. There will not be any difference in the solution.
Mostly.
Okay.
Excuse me, ma'am. I have a doubt on that current number. That's we have discussed about that 1D type, meaning it is a U delta T by delta X. If it is a 2D or it is a 3D case, then how is the current number for the
similar in every direction you will have that criterion applied. There is a particular form.
Then it will be U delta T by delta X plus V delta T by delta Y plus VW delta T by delta X, or how though?
You can search, it's available online. It won't be plus, it will be a combination of these.
Okay.
Okay, you can just say CFL for 3-dimensional coordinates, you will get it.
Okay.
And but something to add, anyway, you will have to take the CFL criterion basis the most limiting criterion. Do you understand what I mean? If you have 10 cells and your CFL in 9 cells is 0.5. But your CFL in one important cell is 1.2. Then that is your limiting cell. You have to work on that. Got it? So even if you calculate the code, like every iteratively, some of these codes display the CFL numbers. You will see it calculating a CFL number, but that's the limiting CFL number that it's calculating. In some cases, these cells might be in some part of the domain which is not important. So even then your code will run. Okay. Any other questions?
Hello.
Huh.
Ma'am, can you explain the difference between the simple algorithm and Pimple? I think we use in Pimple we use both the combination of simple and piezo to solve it.
Yes.
The system, and in some of the cases was mentioned that we can use CFL number, coordinate number more than one in case of Pimple.
Yes, only because the solver permits it numerically. But if you see, it is only allowed but not recommended. You still need to remain under one for a good simulation. None of an SEFD expert will even touch you if you do CFL more than one, even using the Pimple solver.
Okay, ma'am.
Okay, so I think if there are no further questions, I will let you guys continue and finish up, and hope you have a good workshop. I'll see you day after tomorrow, first half with heat transfer. And of course, you can keep asking questions. You can let Payal or me know if you have any further questions. Okay?
Hello, ma'am.
Yes.
Yeah, I have one question.
Hmm.
So in this finite volume solution file,
Hmm.
so we have added p reference cell and p reference value to 0, 0. So like he mentioned that like it's to use zero gradient boundary condition, like, but we have done that in the boundary conditions already. I don't understand why we are doing this here. So can you explain that?
Good question. So PREF typically for different applications later on in Navier-Stokes when you're solving natural convection like flows, it becomes important. See, right now you're only doing a very basic condition of lid-driven cavity, correct?
Right.
Where you are setting an overall pressure, right? And it is only saying that there is redo gradients at the walls, right?
Right.
In some cases, you might not have a reference value of pressure basis which calculations have to be made. Okay. In those conditions, you would help the solver solve the pressure equation better by giving a reference pressure for complex situations. But here we don't need because it's a well-defined problem.
Okay, and then pref cell is the cell identity, or what is that?
I forget now what you're actually referring to. I would presume every cell's pref.
Okay, okay, I got it. Yeah, yeah. Thank you, ma'am. Thank you.
Okay, so I will close for now and I will let the team continue. Okay, thank you guys. Thanks.